Welcome back. Good afternoon. For this session, we have 3 talks. The first talk is an invited talk by Professor Mike Watts from MIT. He is a principal investigator in the Research Laboratory of Electronics and a faculty member in the Electrical Engineering and Computer Science Department at MIT. He has got his bachelor's degree in electrical engineering from Tufts University in 1996, and his master's and PhD both from MIT in 2001 and 2005, respectively. In 2005, he joined the Sandia National Labs, and he was there till 2010, where he returned to MIT as an associate professor. His research interest focuses on photonic microsystems for low power communications, sensing, and microwave photonics applications. And today he's going to talk about electronic-photonic integration within switches and routers.
Thank you. Well, thanks for having me here. This is a different crowd than I normally talk to, and certainly you all know more about switches and routers than I do. But hopefully I can communicate progress within silicon photonics that I see entering into switches and routers in the relatively near future. So, as I'm sure everyone is aware, there's fairly significant logarithmic scaling in the performance of the world's top supercomputers. This is an old chart from the top 500, but basically it points to the fact that as you go out to around 2018, 2020, we're expected to get to exascale compute systems. And while the CMOS continues to scale with Moore's law, at least for the present time, and you get greater and greater computational efficiency, essentially for free, sort of 2x every 2 years. The problem is that there is no Moore's law for communications. And so what you find is that if you try to keep a balanced machine as you go out to exascale and try to keep something close to a byte per flop or even a few tenths of a byte per flop, then you, at exascale, my mic turn off? At exascale, you need to send around close to an exabyte per second. And with present efficiencies, of course, this becomes a problem. If you look at the world's data centers, these are actually even larger machines. They scale out to, I think, around 500,000, at least 500,000 cores today. And they use more power. The largest of these machines consumes on the order of 100 megawatts of power. They cost on the order of $1 billion. And they consume a couple % of US electricity in aggregate. The cost of power exceeds the cost of the machine over its 3-year lifespan. And so folks at Google and other data center providers or users are very concerned about the power consumption of these machines. But they're also concerned about, of course, the cost. And while they don't use quite as much bandwidth as a supercomputer, some of these other motivating factors are very important as well. So as was mentioned, I spent 5 years at Sandia National Labs, and I led their silicon photonics effort, but I worked very closely with their computer architects, and I got to know a little bit about the Cray electrical network that they used in their Red Storm machine. And this is a 3-dimensional torus where you're communicating off the 6 faces of a cube. So left and right, up and down the rack, and front and back. And while this works fairly well for electrical communications where you have to regenerate your signals pretty regularly, and it works well for traditional physics codes where you're often communicating only between nearest neighbors, it presents some challenges for graph informatics problems and even more advanced physics codes, where you run into adaptive meshes, for example, as shown in the upper left there. The different colors on that, which may be hard to see, represent different nodes on that machine. And as this brick crushes a can, you see that the different colors come into contact. And as they come into contact, that represents new communication paths on the machine that need to be opened up. And while that's a very small scale problem, if you look in the the bottom right, where foam is being crushed and foam is flying through the computational domain, you end up with almost perfectly random communications in that machine. And similar statistics are found in graph informatics problems, and so when you start to scale up one of these mesh-based machines, you find that you have a very large number of hops on average. So if you went out to exascale, you're looking at probably 100 by 100 by 100 nodes, and it may take 100 hops to communicate one bit across that machine. If you look at just trying to keep that a balanced machine at exascale and making it truly balanced so that you actually have a byte per flop coming in and out of each node, which is maybe a little bit excessive. But when you multiply that out, you find you have 8 gigawatts of power consumed in the machine, even if you're using 10 picojoules per bit transmitted. So just for reference, a gigawatt is roughly a nuclear power plant. So it obviously doesn't scale. And it doesn't scale not only in terms of power, but in terms of cost. So just figuring reasonable cost for wires, you quickly find that you have billions of dollars for one machine in wire costs. So with optics, you can improve on this a bit just from an architectural perspective in terms of cost and number of hops, because you can communicate longer distances. So you can start to implement, for example, tree networks, where it may only take 6 or 7 hops to get through an exascale machine. And just architecturally, even if you don't improve the power consumption of the technology communicating, you reduce that power consumption to below a gigawatt. Here I'm showing a calculation of half a gigawatt. And the fibers or wires that are used in the system are also greatly reduced. But you find you still have a fairly large number of fibers, something like 5 billion fibers in this hypothetical system. And that's because if you look at the communications technology that's being used today, it's based on parallel VCSEL arrays. With parallel VCSEL arrays, if you want to scale bandwidth, for the most part, you're adding fibers. There's going to be maybe 1 or 2 more increases in bandwidth per fiber. But basically, you have to add fibers every time you want to increase the bandwidth. Of course, that presents a problem when you have logarithmic scaling in bandwidth, because you can't add fibers indefinitely. So if you look at an example of this, this is the IBM Blue Waters machine, which was produced for a DARPA effort. And they put optical connections right down to from the microprocessor to the switches, so right off of each of these, I guess you'd call them daughter cards. And they had something like a few hundred VCSELs per switch coming on and off. And so this is sort of this is basically their first instantiation of this technology. And you can see you've already occupied a very large amount of area packaging these fibers in there. And the problem is when you start to think of your server or your computer, even your laptop, you like to spend maybe a couple $100s for your processor, $100 for your motherboard, another few $100s for memory, maybe $50 or $100 for your network interface. And you like to pay that same price every few years when you update it, even though the performance improves every time you get a new machine. and improves roughly by 2x every 2 years. But if you have to add, if you're an operator of a data center and you have to increase your bandwidth by 2x every 2 years, and you're doing so by adding fibers, this presents a problem. The cost of fibers, in particular multimode fibers, has not gone down substantially over the past 10 years, and it's not projected to. Whereas the cost of bandwidth has gone down, and it's come down roughly 2x every 2 years so far. But as you come out to sort of 2015, 2016 timeframe, you hit a crossing point where the cost of the fiber will actually exceed the cost of everything else in that link. So if you try to build an exascale system, you find that you really can't do it with this technology because the optics will dominate the cost of the system. So that's kind of a long introduction to why do we care about silicon photonics. For those of you that aren't familiar with silicon photonics, there's a few motivating factors. One of the early ones was not necessarily connected to CMOS, but due to the fact that silicon has a very high refractive index. And because it has a very high refractive index, you can make very sharp bends if you have a low index cladding. It's almost like a metallic wall. So you can make about a 2 micron bend radius without any loss on that field that traverses the bend. And that compares to glass waveguides, which were the prevailing technology at least 10 years ago and maybe still are, which have about a centimeter to 2 centimeter bend radius. So it's about a factor of 10 to the 4 reduction in bend radius and a factor of 10 to the 8th improvement in component density. It also enables you to wrap these bends around to form rings, and these rings form traveling wave resonators. You can then couple these rings, one ring after another, and form a nice flat top filter response. So it ends up being very useful for wavelength division multiplexing applications. You can make a very compact filter and achieve very nice results. In addition to that, you can potentially integrate with CMOS in the future. That was sort of what was thought about 10 years ago. And actually, these are some filters that we made about 10 years ago. This is actually in silicon nitride, another high-index CMOS-compatible material. And this is a third-order triple-stage filter. Sort of shown in the upper right is our design, and the bottom right is our experimental result. But you can see we get nice agreement between design and experiment, and you can get this nice flat-top filter shape that's important for wavelength division multiplexing. So you can cascade many wavelengths in principle on a silicon chip, a very compact silicon chip, and we're talking about sort of a millimeter square part. And then, for example, bring that up right next to your switch. And it's actually fairly important for a number of reasons to bring the photonics right up to the switch. One is just for alleviating pinout density. Another is that if you have very low capacitance connecting over to these silicon photonic devices, that you can have very low power consumption on both the modulators that are driving the signals and the detectors that are receiving them can have very high sensitivity. So just a sort of simple diagram of what I see, where I see silicon photonics entering. And I see it kind of entering into the switch. I see the switch as the heart of the network. And the silicon photonics will either be co-packaged with a switch processor, 3D integrated with a switch processor, or otherwise very near a switch processor. So I actually see these SFP pluggable modules going away over the next 10 years, and it being replaced with a silicon system that's driven by a multi-wavelength source that's shared across that chip. sharing of the source is fairly important because it reduces the overall cost of the system. And the packaging and production of the laser source tends to dominate these modules. Okay, so how does the silicon photonics work? One of the easiest things to start with is just thinking about the modulators. So the dominant modulators today are based on free carrier effects. So you either inject more carriers into the silicon or you deplete carriers. And doing so changes the refractive index, which changes the phase of the light. And if you implement, for example, an interferometer, and you drive one arm, you change the rate of propagation in that arm and the interference at the output. So this is an example of a Mach center where we have both ports active, so it actually acts as both a switch and a modulator. And it works fairly well, but you end up with something like 10 picojoules per bit because it's a fairly long device. That's about equivalent to what you can do in an entire link electrically today. So it uses too much power for a low power link. To reduce the power consumption, you can go to resonant modulators. So these are essentially these micro rings, in this case implemented in a disk, where we deplete the carriers in that disk, and that changes its resonant frequency. And as it changes its resonant frequency, it introduces modulation for a wavelength that's sitting on the side of the resonance. So we can do that. We can drive these with just a 1 volt drive, consuming only a few femtojoules per bit, and get nice clean eye diagrams, at least up to 12 gigabits per second. We're working towards 25, and I see it going at least to 25 and possibly to 40. So these devices are not only useful for WDM, and that's a compelling motivation, but also, of course, it's a single mode technology, which allows you to transmit on single mode fiber, and you can transmit over very large distances. So this is an example of transmitting over 40 and 70 kilometers at 5 and 10 gigabits per second, and at comparing that to the back-to-back result, at least at 5 gigabits per second, there's very little power penalty. You can also wavelength division multiplex these disks by making the disks just slightly different in diameter, changing their resonant frequency, and then driving multiple disks along a single line. So they work well, but they do have some challenges. So one of the challenges are that you're trying to hit a frequency of 192.01 terahertz or something like this. So you're trying to hit it to a part in 10 to the 4, a part in 10 to the 5. And you have a very small device, and you have layer thickness non-uniformity in your silicon, and that causes the frequency to wander across the wafer. So it's a challenge. There's another challenge, which is the thermal stability of these devices. So as your silicon heats up or cools down, that changes the resonant frequency as well. And it's about 10 gigahertz per Kelvin. So both of these effects have to be dealt with. And our approach is to implement heaters directly into these filters. The heaters are actually in the rings themselves, so they're very low power, and they're very fast. So they have about a 1 microsecond time constant. And we've demonstrated these. We can drive the frequency of these filters all the way across the telecom C-band, and we can do so in about a microsecond time constant as predicted. So they do consume a little bit of power. It's on the order of 4 to 5 microwatts per gigahertz. But they work well, and actually we can also implement control loops that control their resonant frequency. In this case, we put a diode temperature sensor into the device. We changed the substrate temperature by 55 degrees C, and we held the frequency constant by wrapping a control loop around that diode. Now that was an early demonstration, and actually it's not the approach we're taking at the moment. We're focused more on automatic locking mechanisms. So you don't have to know the frequency of your ring. You have your lasers which set the frequency, and then the rings are driven onto those resonances. And this is much the same as clock recovery, whereas every digital link that you have that's over any reasonable distance, you have to recover the phase of your clock. Here we're adding another control loop, which is to recover the frequency of your rings. So we've demonstrated these. Actually, we've demonstrated 2 different loops. They both work well and weren't particularly hard to get working. Of course, you need detectors. Germanium can be grown on silicon. We've done this. A number of groups have demonstrated this. They work very well. There's a demonstration that we made with 45 gigahertz bandwidth, responsivity of about 1 amp per watt, and dark currents that are in the tens of nanoamps. So one of the differences with these detectors is because they're integrated in single mode, they have just about 1 femtofarad of capacitance. And if you compare that to a typical telecom or even datacom detector today, those detectors have a few hundred femtofarads of capacitance. And if you're thinking of trying to build your amplifier, in this case as an example, a simple TIA, you find you can hang a much larger resistor off that transimpedance amplifier if you have a very low capacitance. And because of that, you can drive your Johnson noise voltage down, and you can, in principle, achieve sensitivities that actually bring you to the shot noise limit. So instead of having a sensitivity of minus 18 dBm, you can get sensitivities that are minus 28 to minus 30 dBm at 10 gigabits per second. Now, in order to achieve that, you have to have not only a low capacitance detector, but a very low capacitance integration technology. So either direct integration with your CMOS, which I'm showing here. This is a demonstration where I directly integrated a silicon photonic modulator, shown on the bottom there, with Sandia 350 nanometer CMOS, or a low capacitance 3D integration technique. And this is something that we're working on now, where you make your silicon photonics separately from your CMOS, but then you wafer bond them and drill down small 1 micron low capacitance vias. The benefit of working with 3D integration is that if you try to do direct integration, you end up being tied to a particular CMOS node, because the layer thickness of advanced CMOS nodes, the silicon layer thickness is getting smaller and smaller and does not work well with silicon photonics. So if we try to put it together a power budget overall, I see it pretty easily fitting into about half a picojoule per bit. Getting below that would require addressing the thermal control issues in a more elegant manner. But I think it's fairly reasonable to get to about half a picojoule per bit for your optics, and about another half a picojoule for your CMOS driving them. And just to sort of wrap up the very simple approach, which is basically let's replace our links with silicon photonics links. I see silicon photonics entering into Ethernet standards, particularly the 100 gigabit LR standards, which are currently at 1310 nanometers. And I would expect that to happen in the next few years. You need to have, it seems like 100 gigabits is enough bandwidth that it's getting challenging to do this with other technologies. So it's kind of a nice entry point. And I think the distance that's in these specs requires that you're in a single mode technology. I want to mention a couple other options. These are more researchy topics. But if you if you take a couple of these modulators, couple them together to form a filter, you can drive it in the forward bias direction and actually shift that filter passband by a few hundred gigahertz. And you can use that as a very high-speed switch. So you can route data in the optical domain with sort of nanosecond switching speeds. And this is something that we demonstrated back in 2008. And you can envision aggregating many of these wavelengths and many of these ports to actually route data within a data center this way. And it sounds a little bit far out, but of course, if you look at telecom networks, ROADMs are fairly prevalent. So just looking at how this type of switch would be implemented, you can envision, N ports going into this sort of crossbar type architecture and having the ability to select wavelengths off of each of those ports and pull them out to any of the other ports on the output. And so you have essentially complete freedom to reconfigure where each wavelength from each port goes. And if you think of how that might interface to, let's say, a top of rack switch, of course you could provide all that bandwidth just to one point, or you could break out each of those wavelengths and send them to the different nodes. And if you do the latter, one of the really interesting things is if you have a 32-port switch and you have 32 wavelengths, you have essentially a radix of essentially 1,000 in that switch. Now you're limiting how much bandwidth you can send because you're only sending one wavelength to each server, but you have extremely large radix. One of the other interesting things that I thought I'd bring up is we've been working on all-to-all networks. So when I saw the Cray talk, I thought that was kind of interesting. We've demonstrated pieces of this. I didn't bring the results here, but actually optics on chip works fairly well in an all-to-all configuration. As you go off chip, and if you're starting to transmit through multiple chips, your coupling losses can be a problem. But on chip, we expect we can implement a WDM all-to-all network where basically each core, this is for a multi-core architecture, but let's say each core takes a particular wavelength to transmit on, and then every other core can receive every wavelength. So you can sort of have this loop where you can receive all the data and then select which data you want to use. So just to summarize, I think hopefully I've convinced some people that silicon photonics is maturing. I think it's maturing fairly rapidly. All the devices work. I think really now we're at the point of trying to make system demonstrations. And I think the trouble is that when you go to system demonstrations, you need a lot more money, basically. So you just, it takes a lot more resources and, much larger teams. And things obviously have to work at a different level of maturity than they do when you're doing single device demonstrations. But I think you'll start to see some groups making these system demonstrations fairly soon. And I think the impact will be significant. I think you'll see, essentially no limit to the bandwidth or no immediate limit to bandwidth in silicon photonics. Of course, you can go very large distances. The power consumption can be very low. You can really improve port density and reduce your pin count. It seems to me that 100 gigabit Ethernet is the first standard where silicon photonics makes a lot of sense. And of course, as you go to higher data rates, it becomes increasingly beneficial. Just want to acknowledge my sponsors, DARPA MTO and Sandia National Labs.